Here's the main topic for this chapter. It's a topic called colligative properties. Colligative properties are properties whose value depends only on the concentration of solute particles. And not on what the solute particles are. So from that standpoint, what it means is that any solute particle acts like any other solute particle. And the difference in the value of the property between the solution and the pure substance is generally related to solute particles getting in the way of a couple things, as we'll see. Getting in the way of forming a solid, boiling, or in the third case, when we talk about osmosis, it will be getting in the way of diffusing. Okay. Now, colligative property number 1 is called freezing point depression. The freezing point of a solution is lower than the freezing point of the pure solvent. So, best example of this is going to be using salt on the roads. So, salting roads in the wintertime to prevent the water from freezing into ice. The second best example, and maybe this is the best example, is the same thing, except when you make ice cream, you use water, salt, ice, water, salt mixture. So, salt, water, ice mixture, and I guess we don't need parentheses or quotes there. Mixture for making ice cream. Both of these work by using the salt to depress or lower the freezing point of the water. In the ice cream, it lowers the freezing point enough so that the ice cream can freeze. And in salting the roads, so it doesn't work with ice, but once the ice melts, the salt gets into the water, and then it makes it only freeze at a lower temperature. Now, here's a picture of this process. Yeah, so there we go. And in this picture, we can imagine that we have a solid phase in solution. And our picture of a solid phase has not changed, or at least our simple picture, from the very beginning of this class. It's got three-dimensional order, which I will now draw as two-dimensional order here. And there's a bunch of solute particles floating around, and I'll draw the solute particles as bigger. Doesn't matter what the solute particle is. And here comes another, so solvent particle. Because I should say the solvent is what's trying to freeze here. Solvent particle trying to join frozen or solid phase. And there's a solute particle blocking it, getting in the way. And then what has to happen is the solvent particle has to push it out of the way, or you require lower temperatures and less kinetic energy in the solution before it actually happens. So that's our picture of what's happening here. And the take-home message, though, is that when you have a solute in a solution, that the solute particles lower the freezing point. And what we're going to do is we're going to calculate the difference between the freezing point of the solution and the freezing point of the pure solvent. And it will turn out as directly proportional to the molality concentration of solute particles. So that's why we have a lowercase m here. You'll see I, our Van't Hoff factor, that's the factor for which sodium sulfate had 3 ions. That's an I of 3. And I, as it says, I'm about to fill in, is the Van't Hoff. And let's see if I can get this right. Van't Hoff factor. And to review, so I equals 1 for non-electrolytes. And I equals, let's do a nice one, 4 for iron 3 chloride, at least in its ideal state. And that's the state that we'll consider. We'll consider these as strong electrolytes that break up completely into ions. Oh, and I forgot to mention, so delta TF, that is the change in the temperature of freezing. It is equal to the Van't Hoff factor times the molality times the freezing point depression constant. There it is. And the freezing point depression constant is specific to each solvent, or to a solvent. And here are some different substances, some different solvents with their Van't Hoff factors. And there is one thing that I do, and you will find this on your conversion and equation sheets, is that I do put minus signs in here. And that is because we are lowering the freezing point. Not everybody does that. You have to put a minus sign in sometime, and that's where I do it. KB values, we will see shortly, are for our boiling point elevation constants. We'll see those too. For example, and here we're doing freezing point. What is the freezing point of a 1.7 molal aqueous ethylene glycol solution? I look at this, I see a skeletal structure, I see its formula. This is a non-electrolyte. And that allows us to determine that I equals 1. When I equals 1, and ethylene glycol and propylene glycol are two of the substances that are used in antifreeze. So ethylene glycol being one of them. And we're trying to figure out what is the freezing point depression. Let's see, delta TF equals IM KF. We said I equals 1. My molality is 1.7 molal. And my KF for aqueous says water, minus 1.86. And the units on that are degrees Celsius per molality. And we can calculate this. For 3.16 or minus 3.16 degrees Celsius as our freezing point depression. And then the question might be, well, what is the freezing point of this solution? Well, we know that the freezing point of water is 0 degrees Celsius. So the freezing point of this solution is minus 3.16. So this is a change in temperature. And so if you see an example that doesn't have water, or for freezing anyway, you do have to go through the step of taking that into account for this solution.